Now we would like to talk about logarithmic functions, and the remainder of this lesson and the entirety of the next lesson will be devoted to logarithmic functions. Logarithmic functions are extremely important. And so what is a logarithmic function? What is a logarithm? Well, it is really just the inverse function of an exponential function. So if you have, remember that if you have any number, any positive real number b different from 1, then the corresponding exponential function is 1 to 1, uh, because if you remember the graph, it passes the horizontal line test. These are the graph of the exponential functions. If b is bigger than 1, if the base is bigger than 1, it looks like this. If the b is between 0 and 1, it looks like that. So regardless of what b is, it passes the horizontal line test, so it is a one-to-one function, and therefore is going to have an inverse. It has an inverse. The inverse of the exponential function with base b is called the logarithmic function with base b. And we have a special notation. This is a notation for the inverse function. Instead of writing f inverse for the inverse function of g, or g inverse for the inverse function of that, we just write log, and then there's a subscript b x, and you can put parentheses around the x if you want to. But that is the notation. It's called the logarithmic function with base b, and again, it's nothing else but just the inverse function of an exponential function too. So it's really nothing weird or mysterious. It's just a function that undoes what an exponential function does. So therefore, when you combine it with an exponential function, with a corresponding exponential function, they cancel each other off. So that means that if you have, let's say, g of x is b to the x, and then if you have f of x equals log base b of x, these two functions are inverses of each other. So that means if you compose them, they cancel each other off. So the g and the f cancel and gives you back x. And if you do it from the other side, same thing is true. So the f and the g cancel each other off. Now, writing this out, what that means is that, well, what is f of x? F of x is this. So that means log base b of x equals x. And then what is the formula for g? Here's the formula for g. So I'm gonna now, in the formula for g, wherever I see x, I'm gonna replace it with this. So it's then going to be b to the log of base b of x equals x. So you get this property. So these two cancel each other, you get back x. And then and now if you do it from the other side, you're gonna get f. What is g of x? G of x is b to the x. So I replace the g of x with b to the x. So the left hand side becomes that. The right hand side still stays x. And lastly, what is the formula for f? Well, it is this one. So wherever I see x in this formula, I'm going to replace it with b to the x. So then it's going to look like this. Log b of b to the x equals x. You can put parentheses in there to make it extra clear. And that is another property of logarithmic functions, because an exponential function with base b is the inverse function of a logarithmic function with base b. They cancel each other off, and you get this equation. And when you unravel everything, you get this, which is one of the properties of logarithmic functions. And then when you do it on the other side and you unravel what that means, this composition, you get this relationship, which is another property of logarithmic functions. In fact, these are properties. Let me see. We have them in the next page. We're going to get there, but these are properties 7, 7 and 8, if you see them right here. These are properties 7 and 8. There they are, 7 and 8. Okay, we're going to talk about all the properties of logarithmic functions in a minute, but that is one that follows immediately uh, from the definition of what it means to be an inverse function, that it cancels with the inverse. Okay, so that's two of the properties. What else can you say? Okay, here's another thing that we can say. Because a logarithmic function is going to reverse a relationship. Suppose that we have the function, this one right here, I'm going to copy. Logarithm base b of x. We're going to call y, f of x, we're going to call it y. So y equals f of x. So this means this is equal to y. Now, because again, f, this is an inverse function of g, which is this g, g of x equals b to the x, because this reverses the relationship of g. If you apply, so if you have x as the input and you apply f and you get to the input y, the function g is going to reverse that, and now the input is going to be y, and the output is going to be x. That is a relation between these two things. So if x is mapped to y via f, then y is mapped to x via g, because g again reverses the relationship. So this relationship right here is this one, y equals f of x. So this relationship is that one. So y equals logarithm. Well, let me write it like I have it in a logarithm of bx equals y. And this one right here is, well, I'm applying g, so that means g of y equals x. And then the formula for g is here. So that means when you plug in y in g, you get x. So that means b to the y equals x. And these two are related. So you can go from one to the other. And this is like, you can use one of these relationships to translate it and rewrite it into the other form. These two equations really give you the same information. It's just that the direction in which you're going is different. So this is usually one way in which we can basically translate a logarithmic equation. You can rewrite it without logarithms in terms of exponents this way. And there's an easy way to remember this, which is the way I use all the time to remember this. So again, these two are the same, and the uh, way I remember this is by using a little diagram, which is like a little circle. You go, it's like you complete a diagram. You go like this. Okay, you go like that on the logarithm. So you can write it big. Logarithm base b of x equals y. That means that b to the y equals x. B to the y equals x. That means b to the y equals x. B to the y equals x. And that is precisely what we had over here. So I have it right there. B, the subscript, to the y equals x. You have to complete that circular diagram, and it gives you the translation into an exponential form. That's how you can interpret this. That's why I remember it. Okay, so now let's talk about other properties of logarithmic functions. So we have another property of logarithmic functions. These ones we just discussed. Uh, we discussed those at the beginning. There's this other property. The graphs look like this for b bigger than 1. And the graph of logarithm looks like this for b smaller than 1. And I discussed why the graph of log base b of x looks like that. And it was because it is the mirror image of the exponential. Remember that how do you get to the graph of the inverse function if you already have the graph of the original function? So this is from lesson 19. If you remember, you get it by just reflecting across the line y equals x. So if that is the graph of 2 to the x, which is an example of an exponential function where b equals 2, then the graph is just a reflection, so it's going to look like that. And remember that this graph right here is typical, representative of all graphs um, with b bigger than 1, with base bigger than 1, so they all look similar. So that means the graph of all logarithmic functions with b bigger than 1 look like this. Now, if you remember, this graph gets arbitrarily close to the y-axis. We call the y-axis, to the x-axis. The x-axis was the so-called asymptote, meaning the graph gets arbitrarily close to the x-axis, but never really touches it, but keeps getting closer and closer and closer. When you make that reflection, then it is now the vertical axis that becomes an asymptote, and the graph of the inverse, which is the logarithm base b, becomes arbitrarily close to the y-axis now. That means the y-axis is now the asymptote. It's a vertical asymptote. Okay, x equals 0. That line is now the vertical asymptote. All right, so that's what it looks like. And then if you were to take the graph of the exponential for b between 0 and 1 and do that reflection, you will get that the graph of the logarithm, the corresponding logarithm, looks like this. Okay, most of the time though, I will say that when we deal with logarithms, usually the b is bigger than 1. This is dealing with logarithms where the base is between 0 and 1 is not very common. It's usually the b is bigger than 1. So normally then, when you think of logarithms, uh, you're going to be thinking of this graph. And you should think of this as one of the toolkit functions because it's also a very basic graph. When you think about logarithms, you should immediately know that the graph looks like this. Logarithm base 2, base 10, base e, base pi, whatever, as long as it's bigger than 1, the graph looks like that. All right, don't forget what the graph of logarithm looks like. Has a vertical asymptote, the y-axis, and it increases. It increases. All right, the domain is only between 0 and infinity, so the entire graph is to the right of the y-axis. There's no graph to the left of the y-axis, meaning that you cannot plug in a negative number or 0 in the logarithm because you're not going to get anything. There's nothing there. There's nothing to the left of the y-axis. So that means, again, in the logarithm, you can only plug in positive numbers. You can never, ever, ever plug in 0 or negative numbers. At least not in college algebra. If you do, it's because you're talking about complex numbers, which is more advanced math. In college algebra, the domain is always from 0 to infinity for the basic toolkit function, the basic logarithm, no modifications. All right, the range is from minus infinity to infinity. That is a vertical span, so it goes all the way to minus infinity, and it keeps going up forever. It keeps growing, it keeps rising, so it really goes up forever. So that means the range, or the vertical span of the graph, goes from minus infinity to infinity. And we said here that's the vertical asymptote, the y-axis, or the line x equals 0. And the x-intercept, what you get when you plug in, uh, the value that you need to plug in to get 0 is 1. So it crosses the x-axis right at 1. When x equals 1, you get 0. Okay, so let's do the first example. We're going to use this little diagram of how to interpret a logarithm to figure out certain uh, values right here. Just using the diagram without using a calculator, and the reason is because you need to understand how to work with logarithms, and also because many calculators don't really even have uh, logarithms based to different various numbers, such as 3 or 5. It's usually only 10 or pi or e, sorry. Those are the ones you can find in a calculator readily. All right, so let's figure out what this is. So it says, compute without a calculator, what is the logarithm of 81 base 3? The logarithm base 3 of 81. So what is this? I don't know. So you can call it something. You can call it x, you can call it y, you can call it question mark. Give it a name. Then, according to the diagram says that 3 to the question mark equals 81. That's how you interpret the logarithm. 3 to the question mark equals 81. So 3 to the what number equals 81. And it turns out that 3 to the 4, 3 times 3 times 3 times 3, so 3 times itself 4 times gives you 81. So actually then the question mark equals 4. Okay, 3 to the 4 is actually 81. 3 times 3 is 9. Okay, this is not hard to figure out. 3 to the 4 is 3 times 3 times 3 times 3. 3 times 3 is 9, 3 times 3 is 9, and 9 times 9 is 81. So the product of 3 by itself 4 times is 81. Okay, so 4 works, so 4 is the answer. That means the logarithm base 3 of 81 equals 4. Okay, now let's do this one. What is this? I'm going to call it something now, x. So according to the diagram, 2 to the what, or 2 to the x equals 1/8. 2 to the x equals 1/8. So we have to think, what number should I put in there to get 1/8? Okay, it is not 3, because if you put 3, you get 8. 2 to the 3 is 8, it's not 1/8. So the fact that it's flipped, that means that it should be a negative exponent. 2 to the negative 3 is actually 1/8, because you flip and then you cube. So negative 3 is the number that should be there. So x equals negative 3. And this one, it was 4. The answer was 4 there. Okay, I think now you should pause the video and try to figure out C and D, and then compare notes with me. Okay, let's do it. So now let's call this one x, and we apply the diagram to reinterpret this in using exponents. So 5 to the x equals 1/5. So 5 to the x equals 1/5. So 5 to the what is 1/5. So if it was 5 to the what equals 5, that would be x equals 1. But it's not 5, it's flipped. So that means x should be negative 1. The whole thing is flipped. So x to the negative 1, 5 to the negative 1 equals 1 over 5. Okay, and here's the last one. 10 to the what? I mean, sorry. Yeah, 10, we're interpreting this. I'm going to call it now instead of x, I'm going to call it question mark. 10 to the question mark equals 1,000. 10 to the question mark equals 1,000. So I'm using the question mark like my variable name. So what is then what goes in there to get 1,000? 10 to the what? The answer is 3. Question mark equals 3 because 10 to the 3 is 1,000. So the answer is 3. Okay, so it is important for you to understand how to unravel uh, logarithms and understand how they work, figure them out. Now, amongst all logarithms, not all logarithms are equally important. Amongst all logarithms, the most important logarithm by far is the one that has base e. Sometimes the one that has base 10 is important. Uh, I think engineers kind of use them sometimes, base 10. But really, the most important one in general is the so-called natural logarithm, which is the logarithm that has base e. When the logarithm has base 10, we call that one the common logarithm. So then there's two logarithms that have special names attached to them, base 10 and base e. Base 10 is called the common logarithm, and the base e is called a natural logarithm. And we have special notation for both of them. So the logarithm base e is denoted by ln, which is really the acronym for a natural logarithm, but in French it was backwards. So that's why I'm like that instead of NL. Uh, okay, so in Spanish it's backwards as well. Right, so that means instead of when we have to compute something like this, we usually don't write it like that. We just write ln of x. Or vice versa, whenever you see ln of x and you're trying to unravel what that means, you can rewrite it like this, log base e of x, and then use a diagram. That kind of helps visualize things. But either way, base e, logarithm base e is ln. Then we have the common logarithm, which is base 10. The notation for that is really just dropping the logarithm, the base, the subscript. So whenever you see nothing, that means the subscript or the base is 10. So if I see, so in this example that we just did a little bit above, a little while ago, this one that says logarithm base 10 of 10,000, we could have written this one like this, log of 1,000. When you write log of 1,000, that means that the subscript is 10. It's implied. There's an invisible 10 there. Alright, and again, when you see this, that really means that there's an invisible 10 there. Okay. Now I have to make a comment because this notation that I just talked about right here, this is notation that some scientists, or a lot of scientists, science, scientists and engineers use. It's mostly engineers and scientists as well, but I think they introduced that notation. So scientists and engineers use this notation. Mathematicians do not use that notation. For a mathematician, whenever you see log like that with any qualifier, for us, that really means that there is an invisible e, not an invisible 10. And I mention that because there are some computer programs out there that were built by mathematicians, or some websites, if you start Googling things to learn more, and they will use the notation that I just, for mathematicians, not the engineer's notation. So you have to keep an eye out for that to see what they're using. In our class, we're just going to use the engineer's notation. Okay, now let's talk about the rest of the properties of logarithms. There's a bunch of properties. You have to know all of these ones back and forth like the palm of your hand. If you have to go to calculus, you're going to be using these properties over and over and over, and they're really important for you to know. It's like one of the most important things you should know coming out of college algebra, dealing with logarithms. All right, so here are the properties. So here's the first one. The log of 1 with any base, that is 0. And why is that? Well, if you don't know what that is, suppose we're trying to figure that out, and we apply the diagram, that means b to the what equals 1. B to the what equals 1. Well, anything to the 0 is 1. So b to the 0 is 1. So that means 0 works. So that means the question mark is 0. So that means this is 0. Because b to the 0 equals 1. So that checks. And to do another one, here's this one. What is log of b, base b, suppose we don't know what that is going to be 1, but suppose we don't know. Applying the diagram is going to be b to the question mark equals b, so b to the what equals b. B to the what equals b. Well, the question mark has to be 1 because b to the 1 equals b. So that means this is 1, which is property 2 right there. Logarithms are also injective or one-to-one. That's what that says. And of course, is because an exponential is one-to-one, and the graph of an exponential function is the graph of a logarithm. And if you just reflect in, the graph is going to also pass the horizontal line test. It's going to pass the horizontal line test. You have it right here. So that one passes the horizontal line test. That one, the graph of the corresponding logarithm, also passes the horizontal line test. So that you can see. So that means the logarithm is also injective. So property 3 says basically that logarithms are injective. So if you have two logarithms equal to each other and the bases are the same, that means the inputs, the x and the y, have to be the same. And that's useful for solving equations, just like when we solved exponential equations. This property tells me that the logarithm of a product, you can split it up, but it doesn't split up as the product of the logarithms. It splits up as the sum of the logarithms. And that is because an exponential function takes a sum of exponents and splits it up as a product. So for example, we have b to the x plus y. That is the same as b to the x times b to the y. And the logarithm does kind of the opposite. It takes a product and then makes it into a sum. This one takes a sum and makes it into a product of two things. And then the logarithm is going to do the opposite because they're inverse functions. So it's going to take a product and make it into a sum. Okay. Similarly, exponents take a difference and turn it into a quotient. So b to the x minus y is b to the x over b to the y. Then a logarithm is going to do the opposite. It's going to take a quotient and make it into a difference. So this is the actual property. The logarithm of a quotient is the difference of the logarithms. So you can split that up into two logarithms, but it's by the difference. Logarithm of x over y equals the logarithm of x minus the logarithm of y. The logarithm of x times y equals the logarithm of x plus, not times, plus the logarithm of y, same base. We already discussed property 7 and 8, and the only one that remains is this one, property 6. That's a pretty useful one, very, very useful one. That one says that if you have a logarithm that has inside of it, and you can put parentheses in here to make it clear, a power function, then you can take the exponent of that power function and move it all the way to the front. So let me make that, write that here, slightly bigger. So if you have a logarithm base b, and you have inside that logarithm a power function, like that, a power, then you can take that exponent and move it all the way to the front and say that this is equal to r log base b of x. And this property is very useful, allows you to simplify logarithms a lot. Okay, so we have those. These are the basic 8 properties of logarithms. Again, you're supposed to know these really well, just like you know exponents, the laws of exponents. I mean, by now, you should really know that x squared times x cubed is x to the 5th, and so on. So this is like very basic. Similarly, properties of logarithms are considered very basic. So you should, again, really know these ones. And this second column right here is just the same as this one. It's just that it's written for the special case when the base is e. When the base is e, you don't really write log base e, you write ln. So all of these properties are exactly the same as these ones. We just wrote them using the other notation so that you get used to seeing them in both notations. When the base is e, use ln and not the subscript notation. Okay, here's the very last example. Evaluate these expressions, again, without a calculator, just using the properties of logarithms. Just using the properties of logarithms. Okay. So we're going to figure out what is the ln of the square root of e. Okay. The square root of e, we can rewrite that using exponents. This is going to be ln of e to the 1/2. And then using this property, number 6, you can take that exponent and move it all the way to the front and say this is 1/2 ln of e. Now, ln of e is 1 by this property up here with the b is e. So ln of e is 1. Memorize that. ln of e is 1 and ln of 1 is 0. Memorize that because that's gonna pop up a lot. ln of e is 1. So that means this is 1. So the whole thing is gonna be 1/2. So the answer is a half. Okay, now let's do this one. 3 to the 2 log base 3 of 2. Okay, here, this one is a little bit more tricky. We're going to use the same property that I used here, but backwards. So in this example, I use the property of that I can move an exponent inside the logarithm all the way to the front. Now we're going to do it reverse. We're going to do it backwards. So now I can take an number in front and move it all the way inside as an exponent. So leaving the base the same, these two that you see here, these two in front of this logarithm, I'm going to move it inside the logarithm as an exponent. So this is going to be log base 3 of 2 to the 2. Okay, so I took the coefficient in front of the logarithm and I moved it inside as an exponent. So I'm using this same property, but backwards. All right, now 2 squared is 4. So this is 3 log base 3 of 4. And lastly, whenever you have a logarithm that is an exponent where the base is the same as the subscript of the logarithm, so the two bases, you see here the bases are the same. The base of this exponential function is the same as the base of this logarithm. These two cancel each other off, so that is this property right here, number 8, with b equals 3. So 3 to the log of base 3, those two cancel each other and gives you back what is inside the logarithm, the x equals x. That means this 3 and this log base 3 cancel each other off, and I get back 4. Because remember, these two are inverse functions of each other. That's why they cancel each other. So you get 4. Okay, and then the very last one, this one right here. So let's simplify this. We're going to use again the same property that I used here of taking an exponent and moving it all the way to the front, but backwards, just like we did here. So I'm going to take that 5 that is in front of the ln, and I'm going to move it inside as an exponent. So this is ln of 2 to the 5. I moved the 5 inside the logarithm and I moved it as an exponent. You can do that as long as you move it inside as an exponent. And now I can move this 4 inside this ln of 3, move it inside the logarithm. When you move it inside the logarithm, it moves in as an exponent. So this is ln of 3 to the 4. Now 2 to the 5th is just 32. 3 to the 4 is just 81. Now there's two more things that we could do. These two logarithms that are right now separate, we can combine them into a single logarithm, because when you have two logarithms subtracted like that, that's a single logarithm that is the logarithm of the quotient, the inside. So ln of x minus ln of y equals ln of x over y. So that means combining just those two ln's, that would be the ln of the quotient, 32 over 81. So that's property 5. A difference of logarithms can be compactified or condensed is the word that we usually use. Condensed to a single logarithm, namely the logarithm of the quotient. So that's what I did there. Logarithm of 32 minus logarithm of 81 equals the logarithm of the quotient, 32 over 81. And finally, E and ln always cancel each other off. and that is property 8, this one, that we used actually here with b equals 3, but now we're using it with b equals e. It looks like this when the base is e. So e to the ln, those two cancel each other and give you back x. So this e and this ln cancel each other, and I get back 32 over 81, and that is my final answer. So that is the last example. This was the introduction to logarithms. In the next lesson, we're going to devote uh, the whole lesson to practice all the properties of logarithms more.